In week 3, we're going to take a little bit of a pivot into the theory of probability, which is sort of the underlying foundation of statistics. We're going to cover a few sections from chapters 4 and 5, probability and probability distributions. Section 4.1 seems to be the most heavily tested, and it's also really the most fundamental. So it's an important section for a couple of reasons. I wouldn't be surprised if this section takes us half an hour to get through. So I hope that you're relaxed and situated and ready to do some good learning about probability. Our 5 main topics in this section are outlined here: the role of probability in statistics, types of probability, terminology and notation, probabilities as fractions, decimals, and percents, complementary events, and finally significant results / the rare event rule. Let's open up topic 1. What do we need to know about the role of probability in statistics? Well, first of all, the proportion is one of the most basic statistics or parameters that we'll study in this class. And it, of course, is a probability. For example, what proportion of the students in a school have gotten their vaccination this semester? Probability also helps us to measure the uncertainties inherent in sampling so that we can understand the value of our statistical observations. Okay, so you remember the concept of sampling. We use a sample, which is something that we can observe, to learn about something that's too big to directly observe. So there's always some inference involved, and that means that there's always some uncertainty involved. So in statistics, results are never 100%. There's always percentages of certainty and uncertainty, and therefore it's really important to understand the limitations or the strengths of the results we're getting. Probability can be a very deep subject. And in a lot of statistics classes, unfortunately, the students get hammered with probability that is really way more than they need to know to finish the class. So traditionally speaking, this week 3, is kind of a critical point in the course when a lot of students end up getting frustrated and dropping out. I'll give you a little secret. If you're in my class, I do a lot of work behind the scenes to make sure that I'm presenting you with questions that are fair and reasonable and important to proceed for the rest of the class. So in our class, we will stick to the essentials of Stats 200 throughout the course, and specifically in this probability chapter. So I think the work that you actually need to get through this class is very it's at a very reasonable level, and it's not calculationally demanding at all. I think maybe you'll find the challenges in this chapter will be more conceptual than calculational. All right, that being said, let's start to discuss issue 2, types of probability, along with terminology and notation. Terminology basically means the way we say things, and notation means the way we write it using math language on paper. So probability has different conceptualizations, and I think that it's important to understand what are some of the different nuances of meaning when we talk about probabilities. So first of all, a little bit of notation and terminology here. In probability class, we're always talking about events. An event is something that can be described with a full sentence, like, for example, the next car to enter the garage will be blue. So a probability is always going to measure some basically factual issue that is either true or false, like that one. And that's what we might call an event. And we usually abbreviate events with capital letters, like event A, event B, event C. So when we talk about the probability of event A, in math language, we would just abbreviate that as capital P with capital A in parentheses next to it. So usually when we put something like that in parentheses, we think of it kind of like as a function, and we can use the word of to notate that. Like if you think about functions in algebra class, we would say a function of x. So probability is a function of A, right? Event A has some probability. So when we see this out loud, we say P of A, but that's really just shorthand for saying the probability that event A will happen. Okay, let's talk about collective probabilities versus individual probabilities. When I speak of a collective probability, I mean probabilities that are involved in large sets. For example, we could be talking about sets of people, or sets of buildings, or sets of states, and we might want to find out a probability that a certain person or building or state has a certain property. And we've already touched upon this issue because we didn't use the word collective probability before, but we used the term relative frequency, and they mean the same thing. Also known as a proportion. They all mean the same thing. So a proportion is measured by counting large numbers of things. Now, a proportion is a fraction. It's the number of successes out of the number of trials. For instance, what proportion of the buildings in Solano County, California, are built to current earthquake code? How would we answer that question? Well, first we have to count all the buildings in Solano County, and then we have to count those that are built to current earthquake codes. When we're counting all the buildings, those are called our trials. Okay, so every building has to be counted, and then we have to try each building to see if it's built to code, and if it is, we call that one a success. So when we're done, we're going to have two really big numbers. We're going to have a number of successes and a number of trials, and when we put them in fraction form, successes over trials, that gives us the proportion of buildings that are built to code. In math language, we would write it this way. The probability of event A is the number of successes, we abbreviate it as X, and the number of trials, we abbreviate that usually with N. So this is the notation that we'll most commonly see. Now, it is important to be a little bit familiar with these formulas, because if you're going to use a formula, you need to know which letters go where. And that means that you need to be able to read a sentence or a paragraph and identify something like, oh, so all the buildings, that would be letter N, and that would go on the bottom of the fraction. You see, you need to be able to identify those issues. I call it turning numbers into letters. Okay, so that's the concept of a proportion, which is something that we're already pretty familiar with. How do we count these numbers? It kind of depends on exactly what we're counting. So collective probabilities themselves come in two flavors. There are empirical probabilities versus theoretical probabilities. The one that we just discussed about buildings built to earthquake code, that's an example of an empirical probability. Empirical, remember, means the first time we saw this word was in a context where it didn't make sense, but here it does. Empirical means based on observation. Because in order to find out what proportion of the buildings are built to code, we had to count them. There's no other way to answer the question. You have to go out there and count buildings. You can't just sit here and think and say, I wonder how likely it would be. No, that's not going to get you anywhere. Okay? And that's because whether a building is built to code or not built to code, there's not a 50-50 chance. They're not equally likely events. And that's kind of the underlying issue, that empirical probabilities are necessary when we're talking about events that are not equally likely. Other examples might be brand preference or handedness. If you want to find out how many people prefer Samsung versus Apple, how many people are left-handed or right-handed, it is inappropriate to say, well, you can either be left-handed or right-handed, and therefore each one must be 50-50. One hand out of two, right? It kind of seems there's a certain logic to that, because you only have two hands, and if you only write with one of them, that maybe there's a 1 out of 2 probability that it's the left hand, but we all know from experience that they're not equally likely. And so, in fact, the only way you can really determine how many people are left-handed is to count them. So that's why surveys are so important in statistics. By contrast, there are some probabilities that don't need to be counted out in the field. We don't need to take surveys to answer questions about flipping coins, because we know that when you flip a coin, there are 2 sides, and this time they're equally likely. It is equally likely that a coin will land heads or tails, and therefore, to count the probability of a head, you really only need to know that it's 1 out of 2. Other examples of theoretical probabilities would be like dice. You're equally likely to roll any of the numbers on a die, or boys and girls in a hospital. When a baby is born, I suppose genetically it's not exactly 50%, but in statistics class we'll pretend that it is. 1 out of every 2 babies will be a boy, and 1 out of every 2 will be a girl. So for those kinds of probabilities, we don't need observations. What we do often need, though, for theoretical probabilities is a little bit of mathematical sophistication and some formulas. And this, to be honest with you, is where probability class really gets pretty scary. But I find it to be that we don't need very much theoretical probability to get through Stats 200. So this is where I really pare things down to the basics here, and we won't go crazy with theoretical probabilities. I think it's more trouble than it's worth. Now, before the end of this clip, I want to contrast collective probabilities with individual probabilities, because this is where things really get philosophically interesting. These 2 concepts are fundamentally different, and yet mathematically they must be the same. So when I talk about an individual probability, I'm talking about a probability that does not apply to large enough sets that can be counted. I'm talking about a probability for one person or one sporting event. What's the probability that that guy is right-handed? What's the probability that the Angels are going to win that baseball game? Okay, so you can't answer that question. Strictly speaking, you're not counting anything. And what you're really asking is for a measure of credence. Credence means how confident or certain can we be? Okay, so when we talk about an individual probability, that's strictly speaking what we mean. We just mean how certain are we? Now, that's a pretty fuzzy question, so we kind of need backup plans. And here's the biggest one. If the individual is representative of a known population, the credence should match the counted probability. In other words, if I pick a random guy on the street, say, what's the probability that he's right-handed? Well, probably the smartest way to answer that question is to say, well, I do know from prior surveys that about 85% of people are right-handed. And so I'm going to adopt that proportion and apply it to that guy. In the absence of further information, I'm going to say that I'm 85% confident that he's right-handed too. I'm borrowing that from the population at large. Now that can get tricky because maybe he's a person, but he's also a man, and maybe men and women have slightly different left-handed probabilities, and maybe he's left-footed, and that might affect how likely it is that he's right-handed. Or it might be culture dependent. Maybe right-handedness is different in one country or another. So if this man is a left-footed man from Slovakia, sorry, we're not really sure maybe which population to apply. But anyway, that's the issue. Otherwise, if we have absolutely nothing to count, for example, what's the probability that you'll get an A in this class? There's nothing we can really count to compare because you've never taken this class before. So in that case, you might have to come up with a strictly subjective probability. I'll make the disclaimer here that people have really bad intuition about probability, and that's why it's so important to have surveys to rely on. All right, so that's it for the theory here. I'm going to run through this topic with some calculation examples in the next clip.